Grawastar. A star like a matryoshka doll. The interior of black holes continues to be a mystery to science. Scientists have been trying for years to find out what's really inside. The matter becomes even more complicated when we include so-called gravitational stars in theoretical considerations. Nearly 100 years ago, the German physicist Karl Schwarzschild presented a solution to the equations of Albert Einstein's general theory of relativity, in which the center of a certain object with a very high density consists of the so-called singularity, i.e. the point at which space and time cease to exist in the form we know. And even they partially switch roles. At this point, all known physical laws, including general relativity, no longer apply. The commonly accepted principle of causality no longer applies. All this is, also today, a challenge for the world of science. Black holes, as these strange cosmic objects were named over time, are also characterized by the fact that nothing can leave them, including light. No information can pass beyond their event horizon. Schwarzschild's solution was so bizarre that initially it was accepted mainly as a theoretical curiosity. Hardly anyone believed in black holes. Everything changed when in 1971 the first object was discovered in space that behaved in a way consistent with Schwarzschild's mathematical description. Today, no one doubts their existence. We know that a massive black hole also resides in the center of our galaxy. In 2019, scientists from the Event Horizon Telescope project managed, for the first time in history, to take a photo of a black hole in the M87 galaxy. Or rather, its silhouettes against the background of the center of this galaxy. In 2001, Polish physicists Paweł Mazur and Emil Motola proposed yet another solution to Einstein's field equations, which indicates the possibility of the existence of completely new objects, which they called gravitational condensation stars, or Grawastars for short. Unlike black holes, Grawastars could have more friendly properties from the point of view of astrophysicists studying them. Simply put, they would be slightly less troublesome as real physical objects. On the one hand, the Grawastar would be almost as dense as a black hole, and would have a similarly strong gravitational field. This would make it look like a black hole and behave like one in all practical respects. On the other hand, it would not have an event horizon, i.e. a boundary beyond which no information can escape. And the best part, their interiors would contain no curiosities at all. So what's inside? Gravitational stars would be composed of exotic, dark energy, which exerts pressure against the enormous force of gravity compressing such an exotic star from the outside. This pressure prevents the Grawastar from collapsing into a classic black hole. A certain problem arises when we try to describe the surface of the Grawastar. According to physicists, it is material, unlike black holes, and is to be an ultra-thin shell of ordinary matter, but with a thickness that tends to zero. This doesn't sound entirely convincing. Physicists Daniel Jampolsky and Luciano Retzola from Goethe University in Frankfurt recently presented something even more interesting. a solution to Einstein's equations that describes the existence of a gravastar inside another gravastar. This hypothetical object was given the name Nestar, from the English term nested. Daniel Jampolsky, who discovered this solution as part of his bachelor's thesis written under the supervision of Professor Retzoler, compares nesters to space matryoshka dolls. It's literally a star within a star. The solution also allows for the existence of a whole series of gravastars nested within each other in this way. What is important is that while the gravastar proposed by Mazur and Motola has an almost infinitely thin shell of matter, the shell of the Nestar is clearly thicker. It is therefore easier to imagine, and perhaps even believe, that such an object could really exist. It's great that even 100 years after Schwarzschild presented his first solution to the field equations in general relativity, new solutions can still be found. It's like finding a gold coin on a path that has already been explored by many other people, says Professor Retzoler. The description and results of the research were published in the journal, Classical and Quantum Gravity. A huge, star-studded structure ripples through the Milky Way. Not only is our galaxy, but quite close to the Sun, there is a gigantic structure resembling a chain of gas clouds. There are several 100 million stars in this gas, and millions more are still being formed. The discoverers called this strange object the Radcliffe wave because, when it was first discovered, it looked like a huge wave rolling across the Milky Way. The name also commemorates the Harvard Radcliffe Institute, whose employees were the first to notice the structure. They detected it somewhat by accident, while creating a map of the dust distribution in our galaxy as part of a project aimed, among other things, at mapping in 3 dimensions the locations of so-called stellar nurseries in the galactic neighborhood of the Sun. The discovery took place several years ago. At that time, it was not precisely checked how the stars belonging to the wave moved within it, how quickly and in what exact directions. Back then, scientists simply didn't have observational data precise enough to show that the wave actually moved, like a wave. Now astronomers in the journal Nature have presented new evidence that it is a wave in the most literal, physical sense. In science, the word wave means a certain regular disturbance. A change in the value of some physical quantity, for example pressure or electric field, spreading in a given environment. In this case, we are talking about a wave composed of gas and stars oscillating in time. The stars contained in it alternately rise above the plane of the Milky Way disk and then fall again. We could say that the Radcliffe wave is the largest single gas structure known to us. It extends for 9,000 and is 400 light-years deep. The diameter of the Milky Way is about 100,000 light-years. So this gigantic wave runs through nearly 1/10 of the entire galaxy. At its closest point to us, it is only 500 light-years away from the Solar System. For comparison, the closest star to the Sun, Proxima Centauri, is 4.24 light-years away, and the closest galaxy, the Andromeda Galaxy, is 2.5 million light-years away. A little more information about the Radcliffe wave has recently been obtained with the help of new data collected by the European Space Agency's Gaia probe. After careful inspection, it turned out that young star clusters, which are also part of the wave, rise and fall exactly in the pattern of waves spreading across the galaxy. What's even more interesting is that the wave appears to radiate from the very center of the Milky Way. Thanks to the movement of young stars in gas clouds spread along the wave. It is also possible to trace the movement of the gas surrounding them and thus prove that it moves like a wave. However, it is still unknown what caused or still drives the Radcliffe wave and why it moves the way it does. Hypotheses that could explain its existence will only now be tested in detail. They include both internal causes, i.e. those related to the galaxy, including supernova explosions, as well as disturbances that may originate from outside the galaxy. The latter includes, for example, the former collision of a dwarf galaxy with the Milky Way. Astronomers therefore have an interesting object about which little is still known. Research will certainly continue. A better understanding of the Radcliffe wave will contribute to a more complete understanding of our galaxy, including the dynamics of its spiral arms. The question also remains whether similar waves oscillate in other spiral galaxies.